black holes and BMS frames and numerical relativity. And before I get into really what that means in the heart of this talk, I'd first just like to open this discussion with a perturbed black hole. So this black hole may have been formed by some binary merger or some supernova collapse, but the main takeaway about this perturbed black hole is that it's fairly easy to understand using black hole perturbation theory. So in the early 1970s, my advisor, Saul Tucholsky, as well as his collaborators, discovered that if you have a perturbed black hole, you can actually fairly easily understand how this perturbation is going to behave as the black hole rings down to a state of equilibrium by working in the Newman-Penrose formalism and discovering this equation known as the Tucholsky equation. And so this Tucholsky equation discovers how this perturbation essentially evolves and describes how these fields are emitted by this ringing black hole. And so the main solutions to this equation can be understood as a sum over damped sinusoids, which we call quasi-normal modes. And so the way you come about with this solution, you can really ignore the main details here, but it turns out that this Tucholsky equation is completely separable into its angular, temporal, and radial components. And so what you find is you get these terms here showing up, which are essentially an amplitude term with these spherical quantum numbers, L and M, as well as this radial quantum number, N, which is called the overtone number. Apart from this, you also have this exponential factor with this frequency omega, and then there's also just this basis in which we write the spherical functions. But really, we just want to focus on these first two terms. And so it turns out that this parameter omega, this QNM angular frequency, is purely determined by the ringing black hole. So it only depends on the mass and the spin of the black hole itself. And because of that, we can actually solve for this quantity either analytically by computing certain contour integrals, or if we want to kind of cheat and just do something easy, we can just write a numerical algorithm to solve for it that way. These amplitude parameters, this QNM amplitude, however, depends on the system in which the black hole was formed. So it can be very complex depending on if there was some kind of binary or supernova collapse or what have you. And so in order to figure out what these amplitude parameters should be, we really need to rely on numerical relativity. And so for the purpose of this talk, I'll focus on numerical simulations of binary black holes. Okay, so let's say we observe gravitational wave. We detect GW 150914, the first observation. So here I'm plotting the plus polarization of the strain for a numerical simulation corresponding to the most likely parameters for this event. This waveform is produced by first performing what's called a Kaoshi evolution on some finite region of spacetime encompassing these orbiting black holes. And then we extract the waveform to asymptotic infinity using what's called extrapolation. So I'll explain that in a bit more detail later on. But so we can take this waveform, we can identify the ring down parts, which our QNM model should represent, and we can try to fit the QNM model to figure out what the numerically motivated amplitudes are, compare them to what we see when we fit to the observed data, and see if there's any discrepancies, because this will serve as a test of GR. But it turns out that this is not what gravitational waveforms look like. So I have to apologize on behalf of numerical relativists, because this is the picture that's been presented to the world, and it's incredibly misleading. Instead, gravitational waves are supposed to look like this. So this waveform is the same Kaoshi evolution, but it's extracted to asymptotic infinity using a method known as Kaoshi characteristic extraction, or CCE. And so you'll notice these two are very similar. They both have the same oscillatory behavior, but there's this new effect, which I've highlighted in red, which we refer to as the gravitational memory effect. And so strictly speaking, when we talk about memory in a theoretical aspect, we really mean the difference in this red curve between two different times, usually early times and late times. Okay, and so what gravitational memory kind of represents physically is if you have two initially co-moving observers, as a gravitational wave passes between them, the space-time will expand and contract with the oscillations of the wave. But after the wave has passed, these observers will experience some permanent offset due to this memory effect. And that's kind of highlighted here by this red curve changing its average value over time. Okay, so I'm a numerical relativist. I hand this waveform to some LIGO expert, and they go ahead and take this waveform and try to fit QNMs to it. And if they think about this analysis, they might notice something peculiar going on. And what happens is that when you look at this equation and when you derive it for the first time, there's something special about this exponential factor. And what's unique is that you actually have to require that the imaginary part of this angular frequency is negative for stability of the solutions. What that means is that as you go to late retarded times, this exponential factor will go to 0. Okay, fine, that's just a feature of the model. But if we remember what the numerical waveforms look like, as we go to late retarded times, the waveform reaches some non-zero constant value. So if this Q&M solution is supposed to be an accurate representation of GR at late times, how can we resolve this discrepancy? And so this is the question I'm going to use to really motivate this talk and try to answer at the end of the day. Okay. So in a bit more detail, what I'll be talking about is I'll first introduce what this gravitational memory effect is in a little bit more detail and explain why we expect it to be in waveforms in the first place. Following this, I'll describe what Kaoshi characteristic extraction is and explain why it's able to resolve these memory effects, whereas previous extractions weren't. And then finally, I'll discuss these Bondi-Vandenberg-Metzner Sachs frames or BMS frames, describe how we can fix them, as well as what they enable us to do, namely perform better comparisons to quasi-normal modes, as well as post-Newtonian waveforms. I'll also highlight some future work that's kind of exciting. Okay, so to understand memory, we really have to delve into the work of Bondi, Vandenberg, Metzner, and Sachs, who in the 1960s discovered that the symmetry group of asymptotic infinity is not the usual Poincare group, but a group with a much more rich structure known as the BMS group. And so the BMS group is just this combination of the Lorentz group and this group of transformations known as supertranslations, which are just extensions of the usual space-time translations. And so an easy way to see why this group is a symmetry of asymptotic infinity is through the following thought experiment. If you imagine you have a group of observers surrounding some kind of event, and say they're not all at the same distance from this event, if we have a good understanding of where they're located relative to this event and relative to each other, we could come up with a scheme where we synchronize their clocks. So even though they're at different distances, they receive the same information at the same time. But if we push these observers to asymptotic infinity, then performing this clock synchronization becomes impossible, and we can freely time translate each observer without changing the underlying physics. And so these super translations are exactly that. They're direction-dependent time translations. What's kind of useful is if we decompose these super translations into spherical harmonics on the two-sphere, what you find is that the L equals 0 spherical harmonics are simple time translations. The L equal 1 spherical harmonics are space translations. And then the L greater than or equal to spherical harmonics are these proper super translations, these new symmetries of asymptotic infinity. And so the important thing to note is that there's actually an infinite number of super translations. Okay, well, what's great about additional symmetries is whenever we have additional symmetries, there should be corresponding balance laws relating some kind of charge and some kind of flux. So what you can do is you can take the metric which describes asymptotic radiation, namely the Bondi-Sachs metric. And so you can ignore all the details here. The main thing to note is in this metric, you can identify charges that correspond to these symmetries. Apply Einstein's field equations to obtain evolution equations for these charges, and then realize that these evolution equations you have are really BMS balance laws, which relate to these BMS symmetries. Okay, so again, I won't state these balance laws in detail, but essentially what they say is the following. The first says that the real part of the strain is equal to a bonding mass charge plus an energy flux. And the second one says that the imaginary part of the strain is equal to a retarded time derivative plus an angular momentum charge and an angular momentum flux. And so the reason these are useful is they kind of give us this nice charge flux decomposition of the strain. So if we run a numerical simulation, we can extract the strain, decompose it into spin-weighted spherical harmonics, and look at individual modes to see which are sourced by charge terms and which are sourced by flux terms. So let's go ahead and do that. Here I again have the numerical simulation for 150914. This is the 2-2 mode, so this is the dominant mode of the strain. The strain is in gray, which is kind of hidden behind this black curve. The black curve is the mass charge term. And for this mode, all the other terms are approximately 0. And so what you'll notice is that the 2-2 mode is predominantly sourced by this mass charge term, which shouldn't be too much of a surprise because the mass charge term is essentially the mass multiple moment. So this is really what we would expect to be sourcing the dominant electric mode, which is the 2-2 mode. Similarly, we can look at a mode which has magnetic parity, which would be, say, the 2-1 mode. And we see something similar, where instead of the strain being sourced by the mass multiple moment, here it's sourced by the angular momentum charge, which corresponds to the current multiple moment. So there's nothing too surprising going on here. Namely, we've looked at the two dominant modes. We see one sourced by the mass charge, one sourced by an angular momentum charge. But can we find any that are sourced by the energy flux, for example? Well, if we return to these balance laws, one thing you'll notice is that they're functions of time. And so if we want to think about an energy flux, we know that over the whole span of the in-spiral and merger phase, there's a massive amount of energy radiated in these binaries. So instead of looking at these equations as functions of time, we can just look at them as functions between early times and late times. And when we think of the net change in the strain, what we're really thinking of is a memory effect. And so it turns out that each of these terms can be understood as their own type of memory effect. Namely, the memory in the real part of the strain we call electric memory, memory in the imaginary part we call magnetic memory, and then the memory coming from the charge terms we call ordinary, and the memory we call, coming from the flux terms we call null. So memory's been known since the early 1970s, and so the original terminology that was used, instead of ordinary, they called it linear, and instead of null, they called it nonlinear. And so we've just changed the terminology to make it a little more true of what these terms really mean.
It was known for gravity or was known for electromagnetism?
It was known for gravity. Yeah, late 1960s and then early 1970s is when we discovered the null memory. And so an example of what makes these two different is the ordinary memory. This corresponds to massive objects traveling to asymptotic infinity. So if you have like a hyperbolic black hole encounter, that will induce ordinary memory, which is typically larger than null memory, but we don't see it as much because it's harder to detect these hyperbolic black holes. And null memory comes from null radiation traveling to asymptotic infinity. And so it's typically for bound systems, such as a binary black hole that's locally bound and emits gravitational radiation through gravitational waves. Okay, well, where might we expect this energy flux to show up? Well, for your typical binary black hole system, the energy is radiated uniformly as a function of angle. So we should look at a spherical harmonic mode which reflects that symmetry, namely the m equals 0 mode. So here I'm plotting the m equals 0 mode of a waveform taken from a numerical catalog. This is pretty much what all numerical catalogs look like for their 2-0 mode. And so you'll see it's approximately 0 during the in-spiral. It has some excitations around merger and then decays to 0. But there's no overall net change, right? There's nothing here that would make us think we're seeing a memory effect. So what's going on, right? Where is this memory? Is there something wrong about our understanding of Einstein's equations, or maybe there's just a bug in our code?
I have a simple question.
Yes.
This strain in the numerical work, where is it being measured?
It's being measured at asymptotic infinity.
Okay, so your code actually has coordinates which go out to infinity?
Not quite. So I'll get to that right now.
Okay.
Yeah.
Sorry.
Yes.
A follow-up question to what Ramesh asked. Is this like a time translation that actually gets basically get corresponded to the flux memory, which is nonlinear, and you're talking about that we need to add it there?
That's one possibility, but it turns out we can actually do something else. So I think I'll answer that in just a moment.
Okay.
So the way that waveform was produced is what we call extrapolation. So after we run our simulation of this finite region of space-time, we obtain metric data on some finite radius. And we actually obtain metric data on a series of finite radii. And so what we do is we interpolate that metric data to have a denser grid, and then we fit to it with polynomials in 1/r. And we say, if we take this to asymptotic infinity, only the 1/r term should survive. So we'll call that the asymptotic waveform. But when we do that, we never actually solve Einstein's equations. So when we perform this method, asymptotic infinity isn't on our numerical grid, which could cause problems if there's some kind of nonlinearity going on as the waveform propagates to asymptotic infinity, because this won't capture that. So a better method is to do something more sensical, namely put asymptotic infinity on your computational grid and actually solve Einstein's equations. And that's exactly what Kaoshi characteristic extraction is. So when we run CCE, we take that same metric data, and then we connect it to asymptotic infinity using a null hypersurface, which I've labeled sigma. And if we choose initial data on that first null hypersurface in a clever way, we can evolve this null hypersurface forward in time to obtain more accurate waveforms, as well as all of the Weyl scalars, while including asymptotic infinity on our grid, and actually solving Einstein's equations over the whole region of space. So what happens when we do this? What's the 2-0 mode look like? Well, if we run CCE and we plot the 2-0 mode, this is what we now see. So again, I have the strain in gray, the mass charge in black, and the energy flux term in blue. And so what you'll notice is that in this waveform, the mass charge is still present, and it looks exactly like what we expect from the extrapolation. But we also now capture this energy flux term, which is exactly what we would expect for a memory effect. Namely, this strain mode exhibits some non-zero net change over time. And so I think this gets back to what you were saying is here, this is the actual memory effect we expect, and it effectively goes as the square of the news because it goes as the energy flux. And so that's where this non-linearity comes from. Okay, so now we understand why there should be memory in our simulations. So I can hand this waveform to a LIGO expert and they can do their Q&M bit. Well, here, this is the 2-0 mode now just zoomed in the merger ring down phase in blue. And the orange curve is the best fit Q&M waveform. And so what you'll see is that the Q&M waveform completely fails to fit to this numerical data, namely because it decays to 0 at late times, while the numerical waveform does not due to memory. So what's going on here, right? What's breaking down? What haven't we considered? Well, it turns out the reason these two waveforms are completely different is because they're in drastically different BMS frames. And so what exactly is a BMS frame? Well, to understand that, we should understand how these BMS transformations affect our asymptotic data. So when we act on our coordinates with a super translation, as I said previously, they're essentially direction-dependent time translations. So the way they change the retarded time is they'll just change it by some function on the 2-sphere, let's call it alpha. Similarly, the way in which they change the strain, if you just work with the Bondi-Sachs metric, what you find is that the strain also changes by an angle-dependent constant, with one small change, namely this factor of f bar squared that shows up, and this is called a spin weight operator. So it just changes the spin weight of alpha from being 0 to spin weight -2, which is needed to represent a spin 2 function, namely the strain, which corresponds to a spin 2 particle, you'd think. But there's also another effect that goes on, namely because we have to interpolate the strain onto the original Bondi time. And so what you find is that apart from this mode-dependent constant, we also experience this mode mixing between the super translation parameter alpha and various time derivatives of the strain. And so this will become important later on. But to summary, the two changes we see, there's a constant change for every mode, and then there's also a mixing between modes. Okay, so if this is how we, how the BMS transformations change our data, how might we go about figuring out what super translation to apply? Well, we should think back to what we did for the Poincare case. And so in the Poincare case, right, when we want to map to, say, the center of mass frame, we can compute a center of mass charge and figure out the translation and boost which minimize this charge. Now, if we can map this charge to 0, we'll say we're in the rest frame of the system. So actually, this has never been done in numerical relativity simulations until recently, but this turns out to work incredibly well. So this is the 2-1 mode for an equal mass non-spinning system. And because this is an equal mass non-spinning system, we actually expect this mode to be 0 due to symmetry. And so you'll notice these curves are incredibly small. They're scaled by 10 to the -9. And so to kind of break down what's going on here, in blue, this is the strain just as it is from the numerical simulation. In red, this is a Newtonian-based center of mass expression that's currently applied to all waveform catalogs. So the way this works is we take the simulation coordinates of the black holes, compute their Newtonian trajectory, and figure out the translation and boost which minimize that Newtonian trajectory. But there's two problems with that. One, it uses simulation coordinates, which are highly gauge dependent. And two, it uses a Newtonian equation while this is a full GR picture. And so what you see is that while it improves the strain relative to no center of mass correction, right, it changes the amplitude by 2 orders of magnitude. What I am highlighting with this inset plot, which shows the 2-2 mode, is that the frequency of the red and the blue curves is exactly the same as the 2-2 mode. And normally we would expect the frequency to be half that. So what's going on here is that by applying this Newtonian center of mass correction, we're not really in the center of mass frame because the 2-2 mode is leaking into the 2-1 mode. However, if we map to the center of mass frame using the center of mass charge, which is full GR, what we find is we reduce the amplitude by another order of magnitude, and we also recover the expected frequency. So clearly using this method of fixing the frame using charges works at least for the Poincare case. So can we extend it to the full BMS case? Well, since the BMS, yes?
Sorry, but I can go back to a cell before, just 3 cells perhaps.
I'm sorry?
Just say another story back.
Oh, yes.
Yeah, so I wanted to know, again, I apologize. I'm not sure where does this mixing between the modes come from? Is this general enough for some actual usual transformations I'm just missing in my head? Because it seems like you have infinite amount of these actually, coefficients, and I'm not sure where do they come from.
Right, so there will be an infinite amount of mixing due to this infinite sum, right? And so this infinite sum is just a Taylor series of the retarded time about the original time. So that's all that's going on when where this equation comes from. But so the mode mixing itself is natural, right? We can do this by just keeping everything on the grid, applying the transformation, and then redecomposing it in terms of spherical harmonics. So it's not like we actually have to compute some infinite sum. We can just do everything on the grid and do an interpolation. Does that answer your question?
There's always a mode mixing for these cases, is that right?
Yes.
It's not.
Yeah.
So it's not a particular physical circumstance that demands it.
I see. I guess I was slightly unsure why in the second term the derivative of alpha appeared, while in the first term alpha itself appeared.
Ah, I see.
Can you imagine to have some other term that also include time derivative of alpha of the first order? Or
Well, so alpha
could
is
it be done through integration by part? Honestly, I don't see any integrals. That's kind of like a confusion that I have, whether this is general enough, or can you imagine some, circumstances that you can also have, partial one of alpha and partial one of h or something like that.
So alpha isn't a function of time. It's just a function on the two sphere. So you would never encounter any type of derivative or integral with respect to time of alpha.
Okay. At least the first derivative, like the partial square of alpha in the second term, why it doesn't appear there? In the first term.
So I mean, right, your first term would just be alpha times the first derivative, and then alpha squared times the second derivative, etc. All right, this is just a normal Taylor expansion. But maybe we can discuss it later on. Okay. Right, so we have this understanding of what to do for the Poincare case, right? Minimize the Poincare charge. Can we do something similar for the BMS case? Well, since the BMS transformations simply promote translations to super translations, we can ask, is there an extension of the center of mass charge, say the super center of mass charge? And if we can minimize that charge, would we put ourselves in a super rest frame? And so fortunately, it turns out the answer to that is yes. So what we can do is it turns out that for the usual Bondi form momentum, there's a natural extension called the Moreski supermomentum, where we take the usual Bondi form momentum, which is these first two terms, and we add this term which goes as f squared shear, where shear is just the conjugate of the strain divided by 2. And so you can kind of think of this as dressing the momentum with these soft charges. But really, this is just a kind of natural extension that arises if you kind of look at how this supermomentum behaves. And so when Moreski proposed this idea, he said that if we map this supermomentum to the frame in which it only has a temporal component, which is the same thing that happens with the Bondi form momentum in the center of mass frame, we say that we're in a nice section. And so I just call that the super rest frame because, when we add these words super to everything, it kind of just makes it more fun. But there's one important thing to note about the supermomentum. And it's that unlike the Bondi form momentum, you can never make it exactly 0 over a time interval at least. And that's because if you look at the net change in the supermomentum by just integrating its retarded time derivative, what you find is that it's directly proportional to the integral of the square of the news. And the integral of the square of the news is essentially the energy flux. So whenever there's energy being radiated from your system, it means you're going to have a non-zero supermomentum. So if we're going to fix the BMS frame, we have to do it at a single time. So the question is, well, which time should we do this frame? And so really, there's only two natural choices. The first is to map to the super rest frame using data at space-like infinity. And this corresponds to the frame that post-Newtonian waveforms are in. And is effectively what all observatories really expect their waveforms to be in, because they're not going to expect their binaries to have some crazy exotic passages. They kind of assume that their binaries are very nice. They just sit there in empty space, orbiting each other, and that's kind of the end of the story. The other option is we can map to the super rest frame using data at time-like infinity. And so this corresponds to essentially mapping to the frame of these quasi-normal modes, where you have a black hole that is ringing down and essentially just becomes some state in equilibrium. Okay, so I actually published a paper working how to do this BMS frame fixing. So what we did is we fixed the Poincare charges by minimizing these BMS charges, and we fixed the super translation freedom by actually running an optimization scheme. So at the time, we didn't know what the post-Newtonian supermomentum was, so we didn't really have a way to map to the PN frame using only BMS charges. And so what we did is we restricted ourselves to L less than or equal to 4 super translations, threw them into a minimizer, and figured out which super translations best align the numerical strain to the post-Newtonian strain, for example. But it turns out there's a much better way to do this, namely just minimize the supermomentum, provided you can compute what the post-Newtonian supermomentum should be. So if you have this expression, it turns out that there's something really interesting that was proven by Dana and Moreski. So here I've just written the transformation law for the Moreski supermomentum. Like the strain, it changes by some angle-dependent constant, alpha, with some spin weight operators out front. And you have to scale out by this conformal factor k, which depends on the bonding mass, and this inner product between the bonding form momentum and the radial 4 vector. And so if you want to map to the super rest frame, what you want is you want this Moreski supermomentum to only have a non-zero temporal component, which for this case is always going to be negative m. And so what you can do then is you can choose some super translation alpha as some initial guess. You can essentially rearrange this equation so you have alpha as functions of the target supermomentum and the original supermomentum, as well as this conformal factor k. And so then you can interpolate this right-hand side onto that initial guess super translation. And after doing so, you can then solve for the super translation, which best solves this equation. You can kind of iterate this process. And so what Dana and Moreski proved is that this actually will always converge, provided your gravitational data satisfies some very loose constraints. And what's really nice is that not only does it converge, but it converges to a smooth solution on the 2-sphere. So in principle, you could write some numerical code to do this iterative procedure and then solve for your super translations using this method rather than running some kind of optimization scheme, which should be much faster and more accurate. Okay, so before I get back to this Q&M picture, I just want to briefly talk about post-Newtonian waveforms. Yeah.
This whole procedure is being done pre-merging, is that right?
It depends. So we can either do it.
When you say post-Newtonian, I'm just wondering.
So for post-Newtonian, it's done pre-merger. It's done during the in-spark phase. For the quasi-normal mode comparison, then we do it during the ring down phase. So it depends on, right, there's 2 times. We can do our best approximation to space-like infinity, which is in spiral, or time-like infinity, which would be the end of the simulation.
Okay.
So in a similar sense to the Q&M waveforms, the post-Newtonian waveforms, when compared to numerical waveforms, also look a little bit different. So here, this is the 2-0 mode for an equal mass non-spinning system. And as you can see, there's a similar effect going on, where the numerical waveform is around 0 at early times, while the post-Newtonian waveform is not. And so the reason this happens is when we choose that initial data on that first null hypersurface, we don't really know what that first null hypersurface should look like. And so effectively, our choice forces the initial value of the strain to be approximately 0. Whereas the post-Newtonian waveform, right, understands this full past history of the binary. And so it sets the average value of the strain to be 0 and the infinite past. And so by the time we reach, 1000 M before merger, it will attain some non-zero value here, right, something around 0.02. But based on our understanding of super translations, right, because these two seem to just differ by a constant, we can apply some super translation to minimize their difference. So this result is effectively showing this procedure of fixing the BMS frame for post-Newtonian waveforms. On the horizontal axis, I'm showing 14 different simulations. So they range from equal mass to mass ratio 4. There's different aligned spin configurations with increasing spin magnitude, anti-aligned spins, processing systems, super kick, which is a configuration that produces a remnant black hole with a high kick velocity, and then a similar set for the mass ratio 4 systems, as well as 1509-14. And so these curves with the circles inside, this corresponds to this previous method where we fixed the BMS frame by solving for these super translations using an optimizer and minimizing the L2 norm between the strains, so between the numerical strain and the post-Newtonian strain. And the bars without any dots is this method where we simply map the numerical supermomentum to the PN supermomentum. And so this required a calculation of the PN supermomentum. So effectively what you do is you just look at the integral of the square of the news of the PN waveform, because that's effectively what the supermomentum is, provided you take the initial value to be this negative m. So you can carry out that calculation and then try to map your numerical supermomentum to the post-Newtonian supermomentum that you calculate. And so that's the result shown in blue. And so the vertical axis on this side is just a common error function that's shown in a lot of numerical papers. But on the right-hand side, I just show what the numerical relative error is. So as you can see, the comparison between the two different methods is approximately the same for all simulations, with some slight discrepancies in this anti-aligned system and the processing cases, which we're still digging into. But overall, this agreement between the two is rather remarkable, because this method of fixing the BMS frame using the supermomentum and only BMS charges takes about 30 minutes, whereas the method used to produce these dotted curves takes about 10 or more hours. So it's a huge speed up, and we can actually measure the numerical precision of these left-hand bars, which converges for every single transformation that we want to apply. Also, just as a point of reference, in red, this is the error between the waveforms. When there's no alignment done, it gets a little bit better when we do a usual time and phase alignment, which is everything that's been done prior to this work. But after we apply a full BMS frame fixing procedure, then the error between these waveforms increases by 4 to 5 orders of magnitude on average. So it's rather remarkable how important this BMS frame fixing is for PN waveforms.
So, naive question, can you see the difference between, can you measure the difference between these predictions and the old PN calculated movement of the mirrors in LIGO?
Can you see this in LIGO, for example?
Yes.
So the problem is LIGO is effectively oriented at one point on the two-sphere. So because of that, the super translations reduce to just being a time translation. So the super translations won't have, in other words, you can't really detect the super translation in LIGO.
So it's a sort of zero order effect.
Exactly.
Yeah.
But this is incredibly important when we compare waveform models, where we do have access to all the data on the two-sphere.
So for Lisa, you would see.
Potentially, because it will span a slightly broader angle, but it's a question of how much the super translation differs in the angle that you're spanning. So ideally, what we would do is we would build 10 different Lisas, throw them off in every single direction, and broaden our span of the celestial two-sphere that we're measuring. Whether or not that's feasible, maybe at the end of my lifetime. Okay, so this is what we achieve for the post-Newtonian picture. And this is very important because the whole reason we do this is the numerical simulations are finite in length, right? They're about 4,000 M, which corresponds to maybe 3 seconds. But LIGO really wants long waveforms so they can accurately span their frequency band. And so what we can do is when we run our finite length numerical simulation, we build a PN waveform that corresponds to that simulation, do this alignment so they agree in some window during the early in spiral, and then we can hybridize the two, where we smoothly blend the data. And so what that allows for, it allows us to create essentially infinitely long waveforms, which you can provide to LIGO. Furthermore, when we construct these waveforms, we can build what's called a surrogate model, which is essentially you run a numerical simulation spanning parameter space, so lots of different spin configurations, lots of different mass ratios, and then you interpolate between the waveforms to kind of obtain this model where you can plug in any number you want and get any waveform you want, which is how LIGO can use for parameter estimation and such. And so we haven't released this results yet, but we hope to by the April meeting. But it turns out that if you do this BMS frame fixing, you can produce much more accurate surrogates because the interpolant is now actually interpolating between simulations that are in the same BMS frame. Whereas previously it wasn't doing that, right? It was only interpolating between waveforms in approximately the same Poincare frame. And that introduced some numerical error. So we find that we can actually significantly improve our surrogate models by doing this BMS frame fixing procedure. Okay, so what about this Q&M case, right? This is kind of what we started with. Well, this was the initial plot. So here, right, this is the numerical waveform with the Q&M model with 7 overtones. And so just for clarification, these overtones, whenever you find the Q&M frequency for a given spherical harmonic mode, there's actually an infinite number of solutions corresponding to these overtone numbers. So the fundamental mode is the least damped mode. It's the Q&M that lives the longest throughout the ringing. And then as you increase the overtone numbers, those become more and more damped at late times. So the n equals 7 overtone is really only excited during the first 10m after moving. So here you can see by this plot, which shows the absolute error, these two disagree horribly. But on the right-hand side, what I'm showing is the result when we map the numerical waveform to the super-rest frame by mapping the Moreski supermomentum to only have a temporal component at the end of the simulation. And as you can see, the agreement between the numerical waveform and the QNM model is drastically improved. The other thing we can highlight is that if you were to just take this and say, oh, they differ by a constant, let's just subtract off the final value of the numerical waveform, which is what people did originally, what you see is that you actually don't obtain as good of a result. And the reason why is because of this mode mixing I was describing earlier. Namely that when we map to the super rest frame, we not only obtain the proper value for the initial value of the strain, but we also kind of uninduce this mode mixing that wasn't wanted. And so that's what you see by comparing these black and red curves. In the black curve, we do the full BMS frame fixing, and in the red curve, we just change the waveform by a constant. So you can see that the black curve is much better. To see that a little bit better, we can look at a mode where we expect this mode mixing to be dominant. So the dominant mode of the super translation is the 2-0 mode, the memory mode. And the dominant mode of the strain is the 2-2. And so if we simply multiply those modes together and look at which spherical harmonic mode is excited the most, it turns out to be the 3-2 mode. And so what you see here is the same configuration as the plot previously. But what you'll notice is that the difference between the red and the black curves is even larger now. So this kind of illustrates the importance of really doing this formal BMS frame fixing procedure, because this mixing of the super translation with the time derivatives of the strain really turns out to matter. Okay, so we can do this more generally. This is a plot showing the error between the numerical waveform and the QNM model for various different spherical harmonic modes. In the top, this is the error between the strain waveforms. On the bottom, this is the error between the first derivative, so the news waveforms. And so what you'll notice is that in the green bars, this shows the error when the numerical waveform is just in the center of mass frame of the remnant black hole, and blue is in the super rest frame. So by mapping to the super rest frame, we can drastically improve these errors. And so what this means is that when we fit our QNM model to our numerical waveform, we can be more confident in the amplitudes we're extracting, so that we won't, think we violated GR when really we just weren't using our numerical waveforms correctly. Okay, so this is kind of the main point of this talk. And now I'd just like to briefly highlight something interesting in the QNM community. So there's been this discussion that when we fit QNMs to waveforms, perhaps we're overfitting, because there's an infinite number of overtones. And so if we include all these parameters, you can fit anything you want. There's been a little bit of pushback. So if you fit to the 2-2 mode, for example, with 7 overtones, it turns out that including all of those overtones recovers the parameters of the black hole much better than if you use fewer overtones. So for the 2-2 mode, it seems like we're not overfitting. But what about for these other modes, right? The 2-2 mode is really the most linear of all the modes. What about a mode where we expect there to be some nonlinearities? Well, if you look at this plot and you circle the modes which have the highest error, the first two modes are the 2-0 mode and the 3-0 mode. And so the 2-0 mode is this memory mode we've been looking at. And the 3-0 mode is what we call the magnetic memory. So this corresponds to something called spin memory, which is a different type of memory effect, but a memory effect nonetheless. And so we shouldn't expect the QNMs to model these modes that well, because these modes are intrinsically nonlinear because they have this memory effect, which the QNM waveform shouldn't capture. So this already tells us that if we want to model the ring down, whenever we build a QNM model, we should also add whatever memory the QNMs induce, right? Because whenever we have some QNM that's excited from a ring black hole, as it propagates to asymptotic infinity, it will induce its own memory effect, which we can see in the numerical way. The point that's really interesting, though, is the other modes that exhibit a large error, namely the 4-4 and the 4+4 modes. Because when people talk about these QNMs, they say, oh my gosh, these fits are remarkably accurate. The ring down of these black holes is completely linear, or not completely linear, but very linear, right? We have no evidence that there might be nonlinearities in the strong regime. Well, the 4-4 mode, if we were to imagine some kind of nonlinearity in the strong regime, so as the black hole is ringing, the dominant mode in the ringing would be the 2-2 mode. And if we say, oh, maybe before that 2-2 mode escapes the asymptotic infinity, it bounces around and interacts with some other modes for some kind of nonlinear interaction. What mode would be excited by the 2-2 mode interacting with the 2-2 mode? Well, it turns out that mode is the 4-4 mode or the 4-4 mode. And so this is very preliminary, but if we go ahead and look at the 4-4 mode of a numerical waveform, the numerical waveform is shown in blue. The QNM model with 2 overtones, as well as the fundamental, is shown in orange. And then the QNM model with the fundamental tone, 1 overtone, and the term we would expect from such a nonlinear interaction between the 2-2 mode with itself, namely this square of the exponential factor, is shown in green. And so what we do is we find the amplitudes which make these models best fit to the numerical waveform. And what we see is the mismatch between the pure QNM model and the numerical waveform is about 10 to the negative 2. But if we include this nonlinear term instead of an overtone, then that mismatch is reduced by about a factor of 2. And so maybe that's not the largest difference, but these numbers are both well above the numerical error of the simulation. So this is at least suggestive that maybe there really are these nonlinearities going on, which we would naturally expect due to this very violent physical interaction. And this would really should promote some in-depth analysis to see, can we see this in other modes? Can we see this in other simulations, right? What's going on here? Okay, and so with that, I'll just briefly summarize what I've been discussing here today. So I opened with kind of this notion that we expect this gravitational memory effect to be in our numerical waveforms. For decades, it hasn't been there, and it's because of how we've extracted these numerical waveforms. But now we have a much more improved method, namely Kaoshi characteristic extraction, which we can run. And indeed, we see the expected memory effects, which agree with these BMS balance laws that come from these BMS symmetries. But when we have these waveforms with memory, it now becomes important to really fix the BMS frame. But fixing the BMS frame isn't too daunting of a task. We can learn from our Poincare work that if we compute the corresponding charges for these symmetries, we can simply minimize them or map them to the desired charge to put ourselves in a desired BMS frame, whether that's to compare to PN waveforms or QNM models. And so because of that, by doing this BMS charge fixing procedure, we can perform much better center of mass corrections on our numerical data. We can more accurately compare to PN waveforms, which allows us to build much more accurate numerical surrogates for observatories such as LIGO. And we can also more accurately examine QNMs to extract these QNM amplitude parameters, which are incredibly important for performing tests of GR as well as the test of the node hair theorem. And then there's also this interesting possibility that perhaps there really are these strong regime nonlinearities in our numerical waveforms, which kind of makes us feel a little bit more comfortable that these black hole mergers really are these very violent interactions. And so with that, I'd just like to say thank you, and I'm happy to take any questions that you might have.
Thank you, Keefe. Really nice talk and questions.
This is the obvious question. As I understand it, the memory effect, as the case originally described, after the gravitational waves go past, there is a permanent strain which is left behind.
Exactly.
Right? Fine. Does LIGO actually see this, or can it see this, or is that a silly question?
It's a very good question. So currently, people have performed analyses to determine whether or not LIGO can see memory, and the current consensus is no, they haven't seen it. Shouldn't come as too much of a surprise.
So this is the curve that surprised me, the one that you had stopped. Yeah.
This one here?
That one, yeah. Because I look at the top curve, all those oscillations are tiny compared to this overall shift from memory.
That's a good
one
point.
would have thought that's the guy that you'll see first.
So I think I'm actually going to show this plot because I think it's a little bit more helpful. So when LIGO detects something, right, they detect it in the frequency range, in the frequency spectrum. And so the memory is non-oscillatory, but it does ramp up with some frequency, right? So in principle, you should be able to detect whatever that frequency is. And it turns out that for most simulations, that frequency is about 10 hertz, maybe a little bit below, but somewhere between 1 and 10 hertz, which is right below the LIGO band. So people have estimated that if you want to detect memory, it's going to take 1,000 LIGO detections. So in principle, it is detectable. We can detect the specific frequency we expect from a binary black hole merger that corresponds to memory, but it's going to require much higher accuracy from our observatories. So LISA, for example, should see memory all the time. Should be all over the frequency there. And so that's kind of a question, is how much
So you
memory.
mean the two stations will be left permanently shifted with each other?
Yes, but right, this is incredibly small. And so this is something I've been wondering is, do we have to be worried at all about this effect accumulating over time? Now, the one thing is, because of how the polarization works, the memory will actually kind of randomly walk between positive and negative signs. And so it's a question of how much will that random walk stray from zero? And is that enough to offset the alignment of the LISA detectors? Probably not, but it might be interesting for someone to do an analysis of that. As for LIGO, though, because the detectors aren't really free falling,
Yeah, exactly.
it might be that the actual setup of LIGO makes it even harder to detect memory than we would actually expect. So I kind of would be surprised if we see it in LIGO. Maybe once the Einstein telescope comes up, that could be a possibility. But what would be really interesting if we build a detector specifically for memory, because you can build such detectors, especially to detect other types of memory. For example, spin memory requires what's called a Sondiac interferometer, which is essentially you have counter-orbiting beams that detect a gravitational wave. So it is possible, but it probably won't happen for another 5 to 10 years.
Incredible.
But it will be an interesting probe of asymptotic infinity, for sure. Yeah.
So I follow up to what you just said. Could we, for other types of memory, could we build ramp-based detectors in principle?
So in principle, right, the LHC should be a detector of spin memory, for example. If we have these counter-orbiting beams in the LHC that never collide, and a gravitational wave passes between the two, they should experience a time offset due to what we call the spin memory. Now, the question is, can we actually resolve that time difference? Probably not, because the spin memory is even smaller than the displacement memory, which is what we were just talking about. So that will probably require a LISA-like detector. That's what the Sondiac interferometer that I was talking about. So it's possible, but it will require more work. The other possibility is the spin memory has its own unique frequency compared to the displacement memory. And so we might be able to detect that frequency itself just in, say, LISA. But that could be kind of tricky.
Yes.
Since nobody else seems to be asking. The Kaoshi characteristic approach that you mentioned, which is what you use for the ring down phase, right? Because
it's what we use for the whole waveform. Yeah.
Oh, you use it for the whole waveform. Okay. So the way you described it, that is where you take your numerical results, which are on a finite spatial grid, and glue them somehow to something that goes out to null infinity, right? Good. That's the one I'm trying to understand what that means. Is that equivalent to saying that there's only outgoing signals, or is this, I mean, does it remove all the reflected signals, or what exactly?
That's another excellent question. Yes. So when we perform Cauchy characteristic extraction, we have to impose boundary conditions at the world tube and at asymptotic infinity.
Yeah.
So at asymptotic infinity, right, we can say nothing comes back.
Yeah, sure.
What do we do at the world tube? Yeah. So there's an improvement upon CCE called Cauchy characteristic matching, which is currently in development. And so what you do there is, while you're running the Cauchy simulation, you also run CCE, and then whatever waveforms you get bouncing off the curvature on this null hypersurface, you feed them back into the Cauchy evolution. And so currently we can't do that with CCE because CCE is run after the Cauchy evolution. But by running CCM, then we could simultaneously be evolving all of space-time.
Okay. So every time step, the boundary condition itself, you kind of work it out
exactly
self-consistent.
Exactly.
Wow.
And so currently, we've just been testing that for scalar fields on a perturbed black hole, but it seems to be working. So our goal is currently—
How much slower will it become?
So CCE is incredibly fast. So CCE itself, to run, I mean, the waveforms I've been showing have 60,000 data points over time, not including the angular data points. And that takes 20 to 30 minutes. And so CCM really won't be adding that much time onto the Cauchy evolution, because our goal is we're releasing a new code called Spectre, which is an improvement upon the current numerical code. And so Spectre will have CCM inside of it. So it really shouldn't be that much of a speed up or a speed decrease, I guess.
Any other question for our speaker? Yes.
Yeah. Can I ask something? So what you described mapping to PMS frames either in the at null infinity or at space-like infinity, depending on whether you're interested in studying the QNM phase of the signal or the post-Newtonian phase, right?
Right.
And then for the QNM, you said doing that can be at least as good, if I understood well, as changing the number of overtones you're picking. Right?
So what I was saying is from these plots, or this is a better example. So the black curve is when we do the actual BMS transformation. The red curve is when we just change the waveform by a constant so that the two agree on the final value. So essentially just subtract away the memory. And that's the red curve, and you can see it's not as good because when we apply a super translation, we have the mode mixing that the constant subtraction doesn't account for.
Right, but the QNM overfitting problem that
Oh, the QNM overfitting problem. Yeah.
in the numerical relativity community.
Right.
That's, if I understand it well enough, that's basically the question of people not knowing exactly where to cut the signal and call it the QNM phase and how many overtones to fit into, right?
Yes. So if you look at this, so this decomposes the strain into this mass charge term, is in black, and this energy flux term in blue.
Right.
So there's no reason the QNM model should capture this blue waveform. And so if you look, right, typically we start our QNM models at 0. And so there's a massive amount of the contribution from the blue curve that the QNM model is going to try to fit to. So when we include 7 overtones, what's going to happen is the 5, 6, 7 overtones are going to try to model this memory effect, which they have no business modeling.
Right.
So really, we should just be modeling this charge, this multiple moment charge with the QNMs.
Right, good. So my simple question is there a flip side of this story in the PN phase?
No, because the PN waveform has memory in it. So the PN waveform in principle should be capturing all of the GR effects.
Nice.
Right, so for example, if we're mapping to the PN frame, we want to align the 2 0 modes. And so here, the 2 0 mode, for example, is entirely sourced by the energy flux, which it turns out the M = 0 modes are pretty much equivalent to the supermomentum M = 0 modes.
Right.
So no, that won't be a problem for the PN case.
Okay.
Yeah.
Any last question? So if not, let's thank Keefe again.
No, thank you.
We have lunch now.
Oh, okay, excellent.
You've earned it.
Yes.